Okay. Okay, cool. So, like Julie said and advertised, I'm gonna be talking to you all about VFDs today. We're gonna talk. We're gonna go over some basics of what VFDs are, how they work, when you decide to recommend a VFD, what you're looking for on a site, how to go about calculating savings around VFDs, and then some really generic costing resources. And then we at the directors conference a couple weeks ago received some feedback that Rutgers would like to see in the reports around VFDs. So I'll talk about what they're looking for there. And then I will go over the cheat sheet assignments that Julie mentioned. And then if there's time, which my guess is there won't be this week, I will go over just pump curves and how to read them in general. And if that just needs to be like a little 5-minute session next week, we'll plan on doing that. So that is the plan for today. So what's a VFD? It is also, or it stands for variable frequency drive. So it's a control component that you add to a motor in order to change its speed. So it's the power going to a motor comes in as an AC signal. Usually in the US it's 60 hertz. And then that 60 hertz determines the speed of the motor. And then if with the VFD, it is able to change that. First it has to go to a DC and then it changes it into a pulse width modulation, which you guys probably, if you haven't already, will learn about in your classes sometime in a controls class. That looks like a different frequency sine wave, like in this photo here. So it makes the motor think that it's receiving an AC signal at a hertz other than 60. And so then it can rotate at a different speed. If you guys are interested more in the electrical engineering part of this and learning more about how a VFD really works, I recommend Engineering Mindsets explanation. They go into some good detail, more than I'm gonna go into today. So, and then just so you're aware, if you see other abbreviations like ASD, VSD, they're all the same thing. It's still variable frequency drive. So once you know that you can change the speed of your motor, why do you want to do that? And where do you see that happening? So motors run all sorts of different equipment: pumps, fans, compressors, agitators for mixers, refrigeration compressors, all sorts of different things. And I got some pictures of different motors. This is not a motor, but different motors running things. And so the idea is that most motors are just at that fixed speed. And then if you're able to slow that motor down, then you can control what's going through your equipment. With a pump, you can control the flow rate. With a fan, you control the air or whatever you've got going through the fan. With a air compressor, you control how much air you are compressing. It's all about the capacity of whatever product you're handling, whether that be water, air, any number of fluids. And so then when your motor rotates more slowly, then you're using less energy. And that's what we're all about, right? Using less energy. So, and then there are some other benefits other than the energy. VFDs have a much better power factor than your typical motor. Typical motors are like 80 to 85%, and VFDs can be between 90 and 100%, just kind of depending on how its induction load works. And then soft start, VFDs can also be used as soft starts. So normally when you start a motor, you've got a huge inrush of current that spikes up your power consumption real quick. And a soft start means that you are slowly ramping up that current draw, and a VFD allows you to do that. So a couple extra benefits. So now you're walking around your site. Where are you actually going to see the VFD? It won't be on your motor. It's not like an attachment to the motor. It's going to be somewhere either nearby or somewhere on the motor control center for that motor. So this photo on top is a VFD that was a couple feet away from a pump motor that we found in a boiler room. And then down here on the bottom, I think actually one of these things might be the complete VFD. I looked at medium voltage VFDs, which are these giant pieces of equipment, but this is also a motor control center MCC, where you're going to have a bunch of different motors being controlled from here. And sometimes that's where you'll find the VFDs. They'll call it a bucket, and you'll just see the control on there. If it has like a hertz or an RPM, then you know you're looking at the right thing. So if you don't see it and the customer said there is one, ask them where it is and you can find it usually. Okay, so now we're getting into questions you should be thinking about when you found some equipment that doesn't have a VFD. When do you want to recommend a VFD? So first thing you want to know is it currently controlled in any way? And usually the answer is yes, you just have to figure out how. So we've got dampers up in this corner, a valve. These are inlet guide vanes, which are more common on fans or compressors. Sometimes it's just turning the motor on and off. You can have recirculation lines where you're pumping your fluid. You're basically bypassing the main process equipment line, and so it's just kind of circulating in its own line, but the pump or whatever your equipment is sees the full flow rate. Pitch blades on fans are another common control, 2-speed motors. These are all potential control methods that you can see. And so and the reason you want to know these is because these also help reduce energy use than just like full flow control, or sorry, not full flow, but like uncontrolled flow. And so your energy savings will be different with a valve versus like an on-off pump. So you need to know that in order to correctly calculate your savings. Oh shoot. Did I lose my, sorry, I was just trying to check the time, but I think I lost my presentation. Okay, are we back?
Yep, it's 1:20, Moriah, so you got
Okay,
25 minutes.
Thank you.
And remember, you got next week too.
Okay. Let's see, where were we? Okay, parameters. Okay, so once you know how a VFD is being controlled currently, you want to think about what parameter it's actually being controlled off of. So maybe it's being controlled by a valve, but that valve is changing based on a tank level, or it's actually measuring a flow rate somewhere and adjusting based on what flow rate it needs. There's many different parameters that you can use, and it really just depends on the process you're looking at. So that's something that you'll have to ask the customer. And then
Moriah, I'm going to ask you one thing to elaborate on.
Sure.
Explain to us very briefly what you mean by differential pressure.
Oh, sure. Yeah, it can actually mean many different things. But I right here was talking about differential pressure across the pump. If you have a pump or a fan, so you're going to have some suction pressure coming in, you'll have a discharge pressure coming out, and then the difference between those two is your differential pressure. If we have time to go into pump curves, then we can start talking about your static head pressure versus your dynamic pressure in your system, which all has to do with what's happening around the pump, not just at the pump itself. So, but yeah, differential pressure, just discharge minus suction pressure, basically. Cool. And then let's see. So another really important thing to look at and know when considering whether a VFD is useful on a piece of equipment is what % of full load is that equipment typically operating at. So is that equipment designed to run at 500 GPM and that's what it's doing like 95% of the time? If that's the case, probably not a good candidate for a VFD. If it's designed to run at 500 GPM or gallons per minute, and it's running at 250, like 3 days a week, it's running at 300 a day, 400 the next, and then 500 1 day a week, then that might be a better candidate because you're at 50% of your design rate. And whatever control method you have, that's probably going to be using more energy than if you slowed that speed down to control down to that flow rate. So yeah, so running at part load often or even constantly is a huge opportunity for a VFD. And then once you know what % of full load it's operating, then the question is, how often is that load changing? Like, is it changing seasonally? Is it changing weekly? Is it changing hourly? The recommended cycle time is not more than 10 cycles per hour, just because otherwise the VFD, I think, can get overwhelmed and you start having issues with the motor too. And I would guess that this is more of a common issue with something like an air compressor, where you see fluctuating use of compressed air throughout a facility at different times of the day. And so you might have more cycling. In a pump and fans, I would think it would be more consistent. But again, that's something to ask your customer, figure out how often things like that are changing. And that's also something you could ask for trends on or measure yourself to try and figure out how often your equipment would be cycling. So that brings us into when you're actually looking at equipment that either doesn't have a VFD or already has a VFD, what are the assessment recommendations that you're actually considering? So the obvious one is just installing a VFD on an existing motor. The motor doesn't have a VFD. It's a fixed speed motor and you've considered all the things we just talked about and it seems like a good candidate. So that's your recommendation. Another one is that you can just install new equipment that comes with a VFD. This is more common on like an air compressor where it's a whole package deal. And then if there are VFDs already on pieces of equipment, that doesn't necessarily mean they're running the way they should be. So that's something to check. They could be not automatically controlled if, there's an operator who's going in there and just like cranking it up whenever or cranking it down, cranking it up whenever he thinks is appropriate, then finding a way to control that could save some energy. Or if you trend the equipment and then you see it's running at 60 Hertz 24/7 or however long the facility is operating, then that's a great opportunity to put some additional controls in and reduce the speed of that motor. Some other things that we've been that we've done recently in assessments is, especially for HVAC fan VFDs, is setting their max % speed to 95% rather than 100, just a way to shave off a little demand in summer months. And then a new one that I don't actually know much about, so if anyone decides to pursue this for an AR, I'd be curious to see what you find, is regenerative capability VFDs. So apparently typical VFDs use brake resistors to absorb power when they're slowing down, but a regenerative one can convert that energy into power that's fed back into the main supply. So I'd be interested to hear more if anyone investigates that. I haven't seen it actually used before. Oh, this is just a general note. If you are logging a VFD, a piece of equipment that has a VFD, make sure that you are not putting the CT in between the VFD and the motor. The reason being is because not only is your amperage changing in that area, but your voltage is changing as well. So your constant voltage assumption that we use from the motor nameplates will not be correct if you put your CT there. So just a good thing to remember and tell your customer when they're installing the CT for you. Okay, we're jumping into savings calculations. So things to consider when you've decided to recommend installing a VFD. And now you are thinking about what kind of information you want to collect and how to go about that. So start by figuring out where are the savings occurring. Are you only getting savings from your motor? Or are you also getting some process savings? For example, on a ventilation fan that's blowing air over heating and cooling coils, if you use a VFD on that, you're not only going to get fan energy savings, you'll probably get some heating and cooling savings too. So always keep in mind what your equipment is impacting. Another thing, considering if demand savings should be included. So if your VFD is running at part load constantly all the time, or that's what you want it to be running at, and right now it's running at full load, then you're going to get that full kilowatt savings in between the difference. But if your VFD or your motor is ramping up and down, and sometimes it runs at max, sometimes it runs at part load, especially during peak demand hours, then demand savings might not be as likely. So, and then I've just listed some other items to consider when you're collecting data, and you guys know here's a nice nameplate. And then pump nameplates are always good to collect because you can use them to look up pump curves and manufacturer information later. So same goes with fan and compressor equipment. So okay, so now we're actually jumping into some equations. So when you are calculating savings, typically the first thing I think about is I want to figure out how much energy I'm using right now. So to do that, there's a couple of ways I could go about that. I could log my pump or fan amperage, and then use, nameplate data, power factor, voltage to calculate my average power consumption. Great way. Totally suggest that if that's an option. If for some reason you can't do that, then these equations are probably your next best bet for accurate power estimations. So what do you need? Mainly you need flow rate and that pressure differential or differential pressure that we were talking about before, whether that's across the pump or static head across the fan. And then if you can get a pump efficiency and motor efficiency, then those you need to put those in, but those are also things that can be kind of you can use some rule of thumbs and not be too far off on those usually, but it will have an impact on your pump power, on how accurate you are if you are able to correctly estimate efficiencies. So yeah, I think I won't read through the equations, but you can see them over here, and I've just included a couple with different units basically. So this fan one has static head and inches of water column and CFM, and then the two pumps one both have flow rate and GPM and total deadhead, that's what TDH stands for, in feet or PSI. So typically I think when I've seen it, pump curves will give you feet of head, but if you're looking at pressure gauges on an actual pump in a facility, those will be in PSI. So yes, we'll move on. So now you've determined your baseline power usage, either through the pump power equation or through logging amperage data. Now, how do you actually figure out what energy you're going to save by using a VFD? The NREL has a protocol that they've come up with to calculate VFD savings, and which is super helpful. So if you're diving into VFDs for the first time, totally recommend that. And I see Rashid has a hand raised.
Yeah, I was asking, are these PowerPoint files going to be available on Canvas after you're done?
I can put them up on Box. Michael, if you can put them on Canvas too, that I don't have
I'll put them on
access to that.
Canvas.
Cool.
Thank you.
Thank you.
Rashid, the other thing keep in mind is we post these recordings to the YouTube channel, to the IIAC YouTube channel. So we got you covered in a number of ways.
Yeah, awesome. Yeah, so I guess, yeah, there's some links here. So reference these files if you want to find that, or I think you can also just search NREL VFD evaluation protocol, and it's one of the first things that comes up. So I found this useful, and this is the main thing that I found useful in them is curve fits. So this is a way you can even use this to estimate your original power draw if you don't have either the pump power, the information to use the pump power equation, or that measured amp data. This is another way that you can estimate your baseline energy usage, but it also has these VFD curves. So basically they've done some tests and drawn curves between percent of flow capacity and percent of power usage. I should have included, there's graphs that you can see that make this more clear. I should have included one, but I could add that in too so you guys can see it later. And then they
Moriah, I
yeah.
just want to give you a 10-minute heads up.
Thank you. And so basically all you need to know, if you already have your baseline power, you just go in with if it's a pump, you go into your VFD and put in your average percent flow capacity. So if you have, if you're typically running 250 gallons per minute and it's designed for 500 gallons per minute, then you're at 50% flow capacity. You put that into this equation with these three correlation coefficients, and then you can get your estimated power usage with a VFD. So you could do that with a fan or with a pump. Yeah, I think this is just kind of a pretty simple, straightforward way to be able to estimate your power usage. And I guess don't forget that it's giving you percent of full power, so you still need to multiply that then by your motor horsepower in order to get your actual power usage. So, okay, then everyone's favorite, affinity laws. So a lot of you probably have seen these before, but we'll just go over them again real quick. So flow rate is proportional to your speed. And so this is super key in you looking at a VFD, because then you can say, okay, if I'm at 50% flow rate, then I'm going to be at 50% of my speed. And my motor says I have a 3,600 RPM motor. So then I'm down to now 1,800 RPM with a VFD. And then you can take that into this third equation, which says that power is proportional to the cube of your speed and or flow rate. So then you can say, okay, well, at 50% of my flow rate or 50% of my speed, cube that, and then multiply by that, again, baseline power that you have taken to get your new power. So I kind of just talked through that, but does anyone have any questions on affinity laws that they've come across while trying to do some calculations, or this is the first time you've seen it and it's a little strange to you?
I guess I have a quick question.
Yeah.
I know that at times there's like raised to the 2.7 instead of to the 3 or different numbers. Could you briefly explain why that is or where that comes from?
Yeah, for sure. So I do have this bullet point there on that. The power exponent that you use the cube root is only accurate if there's no flow control. So if you have absolutely no flow control, no dampers, no valves, etc., then the cube root is what real life looks like. But since in normal pumps and fans have dampers and valves, that power exponent isn't quite correct. And so we use that adjustment factor to use a 2.4, I say between 2.4, 2.7, you can kind of determine what you think is best for your situation. And yeah, that should help you be a little more accurate. Yeah, it's just kind of, these are theoretical, like,
So Moriah, when you
yeah.
say depend, so Moriah, so you say depending on your situation, when would be a good time to use 2.4 rather than that 2.7?
Great question. I would say, honestly, I've kind of done it based on actual measured data. Like if you can, if you have any baseline measured data to kind of compare for maybe another situation or another piece of equipment that is on a VFD. But I honestly don't have a great answer for you, unfortunately. I guess when I feel more sure about something, like I feel more sure that that like my my percent capacity that I've estimated is correct, then I might be a little less conservative on my exponent. But if I feel like I have had to estimate a lot of the different components going in, then I'll use a more conservative exponent. So Julie, I see you unmuting. Do you have a better answer?
Oh, I was just going to step back and say the point of the conversation is to recognize that what those affinity laws are shown in your books are in the theoretical situation where there are no controls. And so making a point to make sure that you adjust them when you identify the controls that are in place is more of the point than the actual number itself. Moriah, I was also going to just say it's 1:41, so we probably at this point need to call it good on this week. Jump to the LLC scopes of work specifically, and then you can pick up next week.
Cool. I think I have 2 slides left anyway, so that works. The only, let's see. Oh yeah, the only 2 things I have left to go over were costing resources, which you guys can go back and look at. And then just the things to include in your report from Rutgers. So again, that's just something you can go back and look at and make sure when you're writing your ARs that you have these pieces of information in them. So to our LLC 1 and LLC 2 scopes of work. So I think it's just LLC 1 does cheat sheet 1 and LLC 2 does cheat sheet 2. So for the first one, the assignment is to create on-site guidance for assessment teams who are considering VFD recommendations. So basically set them up for success. Like what do they ask the customer? What factors are they evaluating as they look at whether a piece of equipment is a good fit for a VFD? What kind of data logging do they need to do? What other data do they need to collect? And then the second one is they've got all that information. They've decided they want to install VFD, create a step-by-step calculation guide on how to perform savings calculations when you're recommending installing a VFD. And if you're super fast at that, then you could include some calculations for other VFD related recommendations. So I'll leave that up, but are there any questions with our remaining couple minutes?
And again, we'll get these materials posted to Slack so you guys can have them there for reference. But we do have a minute or two if any of the teams want to ask Moriah some clarification on these two cheat sheets for next week.
I have a quick question.
Okay.
I guess you'll post it, but I kind of missed the teams. So are you gonna post that on Slack?
Yeah,
The
we'll put those
Okay.
up there. And basically, Parker, you all self-selected, so I did not pick those. Those were
Oh, is it-
self-selected.
Was it the same teams that we selected?
Yes. Yep.
Oh,
So
okay.
most of them are already on Slack, but yeah, we'll get all the materials from today posted there,
Okay, sounds good. Thank you.
as well as the template that Michael worked on to give you guys a place to start with on these cheat sheets. And by the way, anything that you all consider helpful to your teams and your peers to doing this work is encouraged. So visuals are fantastic, pictures are fantastic, diagrams are fantastic. All of that is fair game in how you're developing these. Good question, Parker. Does anybody else have any quick question for Moriah before we call it good for this class?
I had
have
a
a-
quick question.
Okay.
Sorry, Jake. Go for it.
Yeah, I just had a question about turn down. So I think you had a slide that said like 20 hertz was on the low end of turn down for VFDs. And then I've also seen like you can do 20 hertz on a pump motor, but then you still might not be pumping any liquid. It just won't be enough power. Do you have any like guidelines for that?
Yeah, that's where the pump curve comes in. You need to look at the net suction. It's like net dead pressure suction head. I don't think I said that right, but it's basically like the minimum flow rate to keep the pump from cavitating. And cavitating means like your pump is basically eating itself because there's nothing going through it. So basically based on manufacturer specs, that flow rate should align with some minimum speed of the motor as well. And that would be and then also to your hertz. So it really depends pump to pump, I think.
Jake, it's a great question. We can also use a little time to specifically address that more next week. It's worth a little bit more time. There was somebody else
Okay.
that had a question.
Yeah, I have a quick question.
Okay.
So I'm pretty sure that the group that I was in that you posted wasn't the same group that we talked about in class. Like the group, like Lizzie posted a list. It was like Lizzie, Parker, Tess, but I feel like that wasn't the group that I was on. So was there another place where we posted groups that I was just missing?
Is this Jace, by the way?
Yes, sorry.
Jace, let's talk offline and get that answered for you, okay?
Okay, sounds good. Thank you.
All right. Thanks for the extra few minutes here, and we'll resume touch base on some of this content next week and then go into the cheat sheet. So thank you all. We'll be in touch with some more information.
Thank you.
Happy weekend.
Thank you.
Thank you.
Thank you.